So there is more things to say about matrix models of this type, where the matrix has these specifics, meaning that there are a lot of zeros in this type of matrices, right? So the first row is not necessarily a row of zeros. There could be some zero entries there for these fertilities or fecundities. And then this sub-diagonal, maybe you should highlight it kind of more in a staircase fashion, right? So that sub-diagonal contains those values of survival probabilities, but then there are zeros everywhere else. And that's what that's the reason why this type of model, when the matrix has that specific format with a lot of zeros, is the type of family of models that's called Leslie matrix model, or simply Leslie model. Okay, and so we still have a few more theoretical results to discuss about Leslie models. For example, the solution of the Leslie model, here denoted as x of n. So let's remember, this is a solution of the model that is on the few pages back here, but it's a model that says that at n plus 1, the state variable vector x is of the form a times the vector x of n. Okay, so this is a solution of this type of model. So this is saying that one way of finding that, one way in which that solution, that vector of state variables that contains the population sizes of all the H groups, that is something of this type. Okay, and this type meaning that this is a summation of the eigenvectors. So here, when we write a times v sub j, this would be exactly equal to lambda j v sub j. So this is assuming that there are lambdas called eigenvalues, and each lambda sub j has its corresponding eigenvector here called v sub j, and those v sub j's are precisely the expressions that appear here in this summation. This is saying that the solution of such Leslie model is a linear combination of the eigenvectors. But very importantly, this is a linear combination that involves the eigenvalues, but not only involves the eigenvalues, it involves powers of the eigenvalues. So this, this part here, this part is extremely important. So this is saying that this is a lambda sub j to the n, and n is the time step. So at the n time step, that solution x at n is something that is going to be influenced heavily by the nth power of every eigenvalue. So this is j going from 1 through m. So lambda 1 to the n, lambda 2 to the n, lambda 3 to the n, every single eigenvalue raised to the nth power is making a contribution to the population size, the population sizes of all the H groups. Okay, and so this here looks kind of distracting. C sub j at 0, that's a coefficient, supposed to be a time-dependent coefficient. It's a way of expressing it, you know, but I think the message you should take home is this is a linear combination, that vector of state variable vector containing all the numbers of population size for each H group is a linear combination of the eigenvectors that is scaled in a way, or reshaped by the powers of each eigenvalue and of the Leslie matrix. So this inevitably is the type of result that is very, well, not, I don't know, very, but it's somehow theoretical. It's very important that you go through these lecture notes with a little more detail at your own pace. So there are certain things here that are technical details that you want to really make an effort to understand what this is being expressed. But at the end of the day, this is going to end up in providing a result that's called the stable distribution or limiting distribution. Okay, and so the idea is to consider expressions that are going to exploit that fact, that you can write the solution in terms of powers of the eigenvalues. Okay, and this is, again, a lot of technical details there involved. At the end of the day, you can see how when this ratio here, this is the ratio of, remember, this x of n really is a vector, right? And so this is divided by scalar. So it kind of looks innocent right there, but where you consider this in some, excuse me, let me switch colors here. You could consider this as a column vector. So it would be something that looks like this, and this would say that this is x1 over the sum, and then x2 over the sum, the summation, and x3, and so on all the way through the very end, x sub m over the summation. So the summation of what? The summation of the xj's. So xj's here. So what you're dividing here, you're saying that you're dividing every entry of x by the total of all the entries, right? And this is evaluated at the time step in question here, at the nth time step, right? So x1 at n divided by the summation of all x sub j's at time n, and similar for the next entry. So this here is a vector with the proportions, okay? The proportions per age group, okay? And so age group. So what's the proportion per age group? That proportion may be 0.20 or 0.40 or something like that, right? And this is a proportion, but this is still this expression is at time n. So even though it's a proportion at each time step. And so the idea is that is now an expression for such proportion, and this expression you can see here in the numerator and denominator. That's what I strongly encourage you to go over these notes at your own pace to get certain technical details there, but eventually this is going to lead to this result. This is what we're ultimately interested in, taking the limit as the time step goes to infinity. That's called an asymptotic result. Taking that limit, and we find that that limit doesn't depend on n. So this would be taking the limit of that fraction, which is, or that proportion, which is a time-dependent proportion or time-dependent fraction, and this is independent of time here. Okay, so this is still a vector, and that vector is the limiting distribution. So this v sub 1, by the notation that is used here, is that lambda 1 is the dominant eigenvalue, and lambda 1 is associated with v sub 1. So we assume that the Leslie matrix A, when multiplied by v sub 1, is equal to lambda 1 times v sub 1. So that vector v sub 1 is the eigenvector associated with the dominant eigenvalue, and that is the one that goes into this calculation. You have to take the entries of that vector and then do what is called normalize those entries. Add up the vectors, add up the entries of v sub 1. That'll give you a quantity, and then go entry by entry and divide that entry by entry. Divide each entry by the total sum of all the entries of that eigenvector v sub 1. That's going to give you a new vector, which is considered the stable distribution. So here's a numerical example. This may look familiar to you, right? So here there is the you define the matrix, and the first thing is to use this command eigen, and you want to identify first what is the eigenvector with largest modulus. In this case, that turns out to be the very first one, and then you identify. You have to do this here to identify exactly the entry or indices, but this is how you are interested on the eigenvector corresponding to that eigenvalue with largest modulus, which in this numerical example that happens to be the first eigenvalue, whose modulus is something that's a little bigger than 1. The modulus of the other eigenvalues are repeated here, listed here. There are groups of 2 or pairs that have exactly the same value of modulus, because there are 2 eigenvalues that are complex conjugates, and so each of those complex conjugates would have the same value of modules, and similarly for the next two eigenvalues. So, but out of these 5, there is one eigenvalue with largest value of modulus or absolute value, and then the eigenvector we want is the eigenvector associated with that eigenvalue. So what's going on in this part here is that we're precisely extracting that eigenvector, but then we are dividing every entry of the eigenvector by the sum of all these entries. And when we do that, we obtain that's stored in this variable that has this name, stable HDIST, and the values, you can see the values that are stored there, 0.8986, 0.0852, 0.0121, 0.0028, 0.0010, and so on, right? So those are the 5 values. So each of those values is representing a proportion or a fraction that is limiting, okay, in the sense that if we were going to look at the time plots of the fractions, which is not this figure but the next figure, okay, the time plots of the fractions, then each of those fractions as functions of time is kind of settling around a limiting value. Each of those has a horizontal asymptote. If you're going to display that in logarithmic scale, you can see some of the values. So there's one that looks to be almost 1, but that's the one that's 0.89, right? And then there are the other values here. So that's the idea, or this is an illustration with numerical values, an illustration about the stable age distribution, which in summary is how we relate what's happening in that line of code, where you're realizing that there is we're multiplying by 1 over, or simply dividing every entry by the sum of all entries of that eigenvector. And that's exactly what this expression here, number 10, is telling us. You know, that's v sub 1 is a whole eigenvector, and every entry of that eigenvector is divided by the sum of all its entries, and that's what's explained here. Expression 10 is some kind of limiting distribution, okay, and is the fraction to which the population converges as the time step goes to infinity.